Okay, let's come to order. So sorry for the long warm up. I like it though. I like this because it kind of shows you all the different ideas we've been talking about, maybe in a more connected way. We got a little rational root theorem in here. Going back and talking about graphing this, making sure you understand this factorization, what it means in terms of like the qualitative features of the actual picture of the graph, if you wanted to think about that. I like that. Talking about the remainder theorem in C. By the way, in B, is it necessary to, well, by the way, I didn't quite understand your answer. Is it Kevin? I didn't quite understand what you meant. Can you explain? Okay, so what's the 589? Is that what that says? Explain. I'm struggling. Oh, 36 divided by 5. 589 doesn't divide 36 evenly, is what you're saying. Okay. By the way, okay, I'm with you. Okay. Isn't an even number divisor of 36? Okay. All right, I think I understand. All right. By the way, is it possible that a fraction like this reduces, though, and maybe it is a root? Like, keep that in mind, right? I don't think this does, so we're good. But I just wanted to throw that out there. One other way you could do B is, it didn't say use the rational root theorem, is you could actually plug it in, and then, like, a few hours later, see whether it's 0 or not, you know? The rational root theorem is the way to go on B, let me be clear. Okay. Anything else you want to comment on about this warm-up? I just thought of 2 more things to say. Because my head is full of mathematics. Okay. Another thing to think about is, yesterday, remember you criticized me we tested on some problem we were doing, we got -1 as a 0, and then I tested it again, and you were like, wait, why are you doing that? Well, because it could be a root again, right? So we saw here, for example, that -3 works for you, and if you wanted to try it again, you could. It would work a second time in the depressed polynomial. Since it's quadratic, though, second comment, once you find with a cubic even one root, you saw this last night too, right? Doesn't matter how terrible the leftover quadratic is, doesn't matter, right? Even if it's got like irrational roots, you should be able to find them, right? Or today we'll talk about the complex numbers too, and make sure that we're comfortable. So even if that quadratic has non-real solutions, also fine. We should be able to keep going. So as long as we can get it down to a quadratic, like everything's fair game then. Doesn't have to factor nicely. This one happens to though, doesn't it? So that was cool. Okay. Anything else you want to say about life in general? Okay. I have some things to say about life in general. Okay. Thursday's our quiz, and it covers homeworks 1 through 4. So that's tonight's homework. Is the last thing on that. Those who are out tomorrow, I think we'll clean up a little bit from today. Maybe like just do a warm up and try another practice problem and kind of make sure we're feeling good about this. Answer some homework questions, and we'll work on the challenge problems tomorrow. I've been meaning to hand those out, so we'll work on those tomorrow too. So that's why I gave freshmen the challenge problems. Okay. 42. I can't remember. 6 times 9. Complex numbers. Let's talk about complex numbers.
Yes, I love complex numbers.
I think, in fact, we assumed that you already knew something about non-real numbers coming in. Certainly in the context of quadratics, something like that. We gave you some of those on the summer packet. Just like, here's a quadratic, find the solutions, and that may include non-real solutions. So we're going to do that just in the higher order situation setting today. We'll open with the fundamental theorem of algebra. Do you know the fundamental theorem of algebra? Has anyone told you it before today? Is this going to be a big moment for you to learn the fundamental theorem of algebra? Okay, I don't know. I will say it will surprise you a ton, I think. As a hint, does anyone know the Fundamental theorem of arithmetic. I find that people don't know the fundamental theorem of whatever often. So, but theoretically, you know arithmetic, and you don't know the fundamental theorem of arithmetic? Unbelievable. The fundamental theorem of arithmetic says that every positive integer has a unique factorization, right? It has like a thumbprint, or like, right? If you factor a positive integer into its prime factors, there's not like a second way that someone else could have done that would be different, right? So that ensures that like every polynomial is made up of like a unique kind of DNA, right? It's kind of its building blocks. The fundamental theorem algebra is similar. It talks about the factorization not of positive integers, but of polynomials. It doesn't say anything here about unique factorization, but that's a result that's close on its heels, and we'll say that next, actually. But it does guarantee that a polynomial of degree n has n complex zeros, up to multiplicity, though, right? Like we understand, like in our example in the warm-up today, that this has 3 zeros, one of which is a repeated 0, so that makes it add up to 3. So we're good. Right? Am I right that that's not actually a huge surprise? You just maybe didn't know that was called the fundamental theorem of algebra. Now, to the extent possible, I like to be able to justify claims to you. And in a math class, that's what we're in the business of doing, sense making. Unfortunately, the proof of this, even though the statement is extremely simple and intuitive, you even already understand this probably before I even told you, the proof is actually like graduate level mathematics. It's like super, the proof of this is actually super hard. And I have like worked through it before, but like I'm not prepared to like present it to you. You can, I don't know, you can look at it, but it's surprisingly difficult. So
We should do that in class.
that should be like what we do for a couple of days in class, like just figure it out. Yeah, I think it might take a year actually.
Yes, that's perfect.
Like a whole year on just that, yeah.
Yeah.
Next semester, a big one, yeah.
Like a block project.
All right, if you tell me that the first thing is true though, the fundamental theorem of algebra, then this follows immediately though, and that's the linear factorization theorem. Should make sense that if you can find the zeros, and there are n of them for an n-degree polynomial, then you can express it as a linear factorization. That is, by linear we mean each of those things in brackets is linear, isn't it? It's like something like x. It's not x squared. X minus a 0. X minus a 0. X minus a 0. Where z1 through zn, those are my names for the zeros. And why do I know there are n of them? Well, because look up above, right? We already talked about that. Okay, it's fine. I do want to make sure you understand the connection between these fully. I mean, we've been making that connection, I think, a little bit here and there, and you understand that like zeros and factorization are intimately linked. But you know, if I gave you, say, a quadratic and said factor this, I think some people, especially if you're early on in your algebra career, if I said like x squared minus 5x plus 1 or something, I said factor that, go. There'd be some people who say, I can't, it's not factorable. But of course it's factorable, isn't it? What would you have to do? I mean, it would be a little, yeah, if you can find the zeros, then like game over, right? Then you can just write x minus whatever times x minus whatever, where the two whatevers are the zeros you found, right? So just to be clear, could someone ask you to factor that? Absolutely they could, right? We might. You wouldn't hate them. You'd probably like them for making your brain bigger. You'd like that. What am I going to say on this one here? I have complex conjugate zeros is the title of the thing I'm about to say. What do we mean by complex conjugate zeros? Reach back into your knowledge of what we mean by that. You did some complex numbers before. We're putting like everything we know on one slide. Okay. It's good though. Anyone have a result for me? I'll put it up. I don't mind telling you, but I thought maybe you'd remember something about complex conjugates. They come in pairs, right? So if A plus BI is one of the zeros, then A minus BI is called complex conjugate pairs. Yes? Is that ringing a bell? Yes? Okay. Then A minus BI is also a zero. Provided that the polynomials you start with has real coefficients. That's actually an important element. right? So that is to say, if someone shows you a polynomial of this sort, f of x equals I x cubed minus 1 plus I x squared minus 3x or something like that. This doesn't apply, okay? But thankfully, no one will be showing you a polynomial like that anytime soon in your life, so don't worry, okay? All the results today will hold for all the polynomials that we'll be working with in this class, at least. Okay. Oh, that was too fast. I apologize. So, even though we maybe kind of just said things very precisely, am I right that on a larger scale you haven't learned very much yet today? Am I right? I assume these are kinds of ideas that we're formalizing right here on this slide, but it was a nice review. Thank you. Yeah.
And then the test, because we nothing, because the results the review.
So now we just proceed to do all the things we've done before. Now we have complex numbers in the mix, right? All that is non-real numbers might arise in some of the problems. Like your homework tonight will look very similar to your homework from the last 2 nights, except now some of your answers will be non-real, right? So we'll just add that into the mix, right? We still are going to do all the same things we've been doing. In fact, why don't we do another one of these guys, right? Here we go. Right? Just go. Factor this.
What's with you in 5th degree?
Do you I like 5th degree. Sorry.
It's every single time. Always.
What about the warm-up? That was 3rd degree. Don't say always.
Class, the past 3 days.
I just think it's a little more interesting. It's perfect, right? Because the 3rd degree one is not too hard because all you have to do is find one root and you're kind of good. I could use a quartic. That'd be kind of fun. Anything higher than 5th would be kind of a little bit of a laborious process for you. So I feel like it's a sweet spot. We could do a higher degree.
Oh my God! No. Let's go.
All right, go ahead and feel free to work as a team here. I might need your help too. Here. Plus or minus 1. Let's test some of those if they're roots at all. If there are any rational roots at least. And I don't think Descartes is going to help us at all, really. Yeah, let's test them all. Here we go. Doesn't take long. By the way, every time you get a wrong answer, if someone were to ask you to graph this, you actually, every time you get a quote-unquote wrong answer, you are actually getting information, aren't you? If you get something other than 0 down here, what is it? Well, it's the value of the function at that place. So if you were plotting this, you actually did get something useful to you. It's a point on the curve, isn't it? So, just thought I'd encourage you. Okay. So start trying stuff, see if anything works. Holler if you get something that works.
I got something that works.
Hey.
That works. X minus 1.
1 works. Yeah?
Yeah.
So we got lucky right away. We're going to have to do some more testing, though. What else works? 4 works. Okay. I'm just going to steal your idea. Yeah, just check your arithmetic along the way. Ooh, I like it. I think I'm kind of done here. Okay.
Oh, I see it now.
How are you doing out there? But by the way, on the homework, this is what was being asked last night on the homework was actually that you find these zeros, right? A lot of you just wrote the rational roots. I saw not a lot of you, but a handful of you didn't actually do all the work. This is it was a lot of homework. I mean, not a lot. It takes a little bit of work to do these. This is not something you just walk away from. How do you factor that guy? I mean, we could keep going and test some more things. If you're doing that, notice that 4 and 8 are now out, right? If this is your new polynomial, right? And actually, the positive numbers are out too, aren't they?
Yeah, they are.
Because Descartes' rule of signs, this is all positive coefficients, so there are no positive real solutions.
Negative has to be.
All right, well, one way you could do this too is, does this ring a bell to you? Maybe you, yeah? It's what? It's groupable. I like that term, okay. Yeah, feel free to keep testing factors, but if you see any other thing that works, do it, you know. And then if we really are factoring this in terms of its linear factors, then we're not done yet, right? We can't stop at x squared plus 1. We need to factor this like was claimed could always happen. We need to factor this all the way down to its linear factors, right? So how does this guy factor? And then we'll be done. Yeah, and how do you figure out that those are the roots of that? Maybe you just know it. For this simple one, maybe you just knew that. Remember what we said earlier, just a minute ago. If you're not sure what the roots are, solve it, right? Solve that. What do you get? X squared equals -1 plus or minus square root of -1. So there we have it, right? So I think that's my final answer. Did we do what we said? Express f of x in terms of its linear factors. Done. Okay?
Wait, how does the x squared plus 1
Wait, which one? X squared plus 1? X plus or minus sign? How to get from here to here? Yeah, so if you don't know how to factor that, which you don't maybe off the top of your head, then you can find the zeros. Just do it off to the side here. Because like we said earlier, if you can find the zeros, then you have found the factorization. Right, so we have the other two zeros now, I and negative I, and you can put those into the factorization if you didn't know it beforehand. Great. Okay, so this is the kind of thing we'd like you to be able to do, just very similar to last night, except last night you might have stopped here, right? Really, that's the only element now. Now, could I give you something again? Let me ask you, could this quadratic be even nastier? The answer is, of course it could be, right? It could have irrational roots, it could have non-real roots, that'd be fine. You have the quadratic formula to help you along. Okay. How are we doing on time here? Let's just for the sake of time, we're gonna why don't you write this down, but then maybe just do it in like English class later on or something. Okay. After the quiz, yeah, exactly, in English today. Okay. Or history, it's fine, whatever.
How did you know about that quiz? Huh? Is there anything else you're hiding from us?
But I mean, it is kind of fun to see that this works. Again, our task today is just to kind of like remind you that the things you've been doing work in the context of complex numbers in general, okay? Right? So go through and do this, and I'll let you finish later. Yeah. Okay. Did you write it down at least? Write it down at least so you can finish it later if I forget. Yeah. Okay. You didn't write it down yet?
You know about the English quiz. What else have you not been telling us?
After the English quiz, you can do it. Work on this. You'll be so bored afterward. You'll need something to do.
Predict when the next stat quiz is.
The next what?
Stat quiz.
Next Wednesday. Really? All right. I'd like to move on to something else here. Okay. Have you done this before? If not, then let's do it for your first time if you've never done this before. Let's actually multiply this out. And I'm trying to do you a favor by putting that extra set of parentheses in there. I think you should kind of still think about this as being two binomials multiplied together. Yeah? Okay, the product of two binomials. Even though technically I guess they're kind of trinomials. But I would actually keep those, at least on the first step as you expand it out, keep those parentheses, those inside ones there. Give it a try. Have you done this before? Pay attention on each step to the structure. Try to predict what the next step will be just by kind of looking at the structure. Lots of nice things happen here. In fact, if those are complex conjugates, which they are, then what do we guarantee about the polynomial that results? The quadratic we're going to get should have what? Should have all real coefficients, right? Like all the i's should hopefully go away, right? So by that I mean, right, like actually just keep them as they are, x squared outside if you like, whatever. Right, that's what I mean. I've just treated it like normal FOIL kind of, and then, right, keep going. Yeah. What is x squared? That's a great question. The definition of I. Right. All right, so do you already see what's going to happen? What happens with these two guys? Yeah, we're going to get a positive 3ix and a negative 3ix. So those will go away, and we'll just be left with what? Negative 2x. So we have x squared minus 2x. And what is that down there? Can you do it in your head? 10 is what you get. So there's our final answer, x squared minus 2x plus 10. Right? So I want you to start seeing the structure. I have it actually revealed for you down here. This will always happen, right? You'll always get, like, if these are complex conjugates, this will always be how this feels. You'll always get twice a here, won't you? Times x. And over here, how do we get 10? Can you give me like a general rule if you have a plus bi and a minus bi?
It's a squared plus b squared.
Yeah, you'll get a squared plus b squared. So I just want you to start like noticing the structure there. Right? This is always what happens. Like, we could do a whole bunch of examples of this, maybe. Maybe we should have done that. Everyone should have gotten a different problem, and you could all examine the structure, how it keeps feeling the same. That's always what happens. Too bad, right? To do lots of different ones. All right, and then remember, like I said, if we have a quadratic of this kind, like x squared minus 2x plus 10, we call this quadratic, if it has only non-real zeros, we call that irreducible over the real numbers. Okay? Have I used that word yet? There it is. The new word then, if we haven't said that yet. And sometimes I'll give you an instruction. I'll say, hey, here's a fifth degree polynomial. Say, factor this with linear factors and irreducible quadratic factors, which is a big fancy way of just saying, on that previous problem, stop when right before you have to go to complex numbers, right? But do you agree that if we're working with only real numbers, we should always be able to get our factorization at least as good as that? Linear and irreducible quadratics. There's never a time when you'll be factoring just with real numbers and come across a cubic that you're like, well, I have to stop here. No, because a cubic always has a real root, doesn't it? Doesn't that make sense? So we should always be able to factor it all the way down to linear factors and possibly irreducible quadratic factors. And if we're dealing with complex numbers, then you should always be able to go all the way to linear factorization, always. Does that compute? So this idea of like an irreducible quadratic is being introduced here on this slide. Hopefully you're good at multiplying like we just did. Hopefully you're also good at going back. If I said factor x squared minus 2x plus 10, you should be able to do that using maybe the quadratic formula for your help. Okay, I have one more fifth degree polynomial for us to factor.
Yes.
I'm just so excited. We have 5 minutes. I think we can do it. And by 5 minutes, I actually need more.
Final countdown.
All right. Sorry, was that good? Are you good? Are you good? What about you? Did you? Are you good? Okay. Huh? It's good. I told you. This is for you. This goes out to Gabe. Okay. All right, here we go. Are you excited about this one?
Yes.
Right? All right, then all these things over 3 also, right? All right, there we go. We're getting good at that, writing that list out. It's not a problem. That's just a couple things to test. No big deal. Again, I'll crowdsource this a little bit. If anyone has one out there, please let me know.
Try it every time. Do we actually have to?
Yeah. Of course.
There's like no easier.
No, it's not gonna work. You have an eraser too. They make those. This was an idea stolen from like the real world. Just so you know. Okay, this whole idea of an eraser. Okay. Well, you can. Yeah. What? Oh, what did I just say?
You added them.
Oh, you're right. Why does that one work? Does -1 work? Silly, Mr. Chase. I was going so quick, you know. I was so excited. I still think it doesn't work though.
But at least it had a chance.
But at least it had a chance. Does Descartes help us, by the way? I don't think it does, right? Yeah. I mean, well, if you just keep going. Anyone have one yet? Let me know. You have one?
I have a factor 3x minus 2. Which one? 3x minus 2.
How'd you get that?
Well, I looked at the equation and I realized you can just group each of the numbers because each of them is like.
Oh.
Because like it's like when you take out.
Yeah, you could do like super grouping. Yeah. That's insightful. Is it 3 halves? Did you say, or -3 halves that works?
Like I said the linear factor. 2/3.
Sorry, 2/3 is what I meant by 3/3. All right, here we go.
Okay, no. So what I did is like I noticed that like wait. Every like odd line is a factor of every even one.
That's cool. All right. We still need to find a 0 though. Another 0. Ah, wait a second. I like this. Do you see what this is? Hold up. I'm loving this. This is 3x to the 4th plus 6x minus 24. Do you think you can factor that x squared? Do you think you can factor that without any other work? Isn't that like quadratic in form? Sorry, the 3 is in there, isn't it? Okay? So I think you can knock the rest out without actually having to do any more tests.
Okay, so chapter 9.
That was
Okay, so he finally goes to Emerson. Emerson signs the letter. It turns out that he was blackmailed the entire time. The letter takes recommendations. They were like, keep this man away from our little hearts. And he wants revenge. He just loves this. This almost like
just like hacking NSA. She all signed it.